Well, we're ready for Class M, the method of Frobenius. Now, this class is more like what you would get in a mathematical physics course, where you look at mathematical methods. This method is a way to solve differential equations, and you most likely will see it again in another course if you haven't already. And this is okay, because a course like mathematical physics explores the math to master the math more, the math that's used in physics courses. So this is great. It's a review and you get to master it. And we're going to use the method of Frobenius for Legendre's differential equation, which is an equation that comes about when you solve the Schrodinger equation and look at the orbital part, and you get all kinds of cool things in chemistry, orbitals and things, but we're not going to do much with the physics, but the method, the mathematical method in solving the differential equation. It's a very, very powerful method to use a power series. To solve a differential equation. Used quite often in quantum mechanics. So let's proceed. Chapter M, the method of Frobenius. Now, this is more like a math physics kind of a class, this particular one, where we take time to look at things that you do see in other classes, but take a break to master the concepts. So this method of Frobenius, there he is to solve a differential equation by using power series. So in other words, the y of x, which would be a solution to a differential equation, is written as a sum from k equal to 0 to infinity of some coefficients ak and x to the k power. So you can think of this as some a0 plus a1x plus a2 x squared plus, and so on. Now I'm going to give you 4 steps in doing this kind of a problem. And I'm going to give them names. Step 1, I'm going to call that series plug-in, or just plug-in. You plug in the series to the differential equation. And if that doesn't work, you can try a more general case. You can try taking the k and replacing the k with k plus r, where r is another value that makes the series more general. And there's other tricks you learn in differential equations. There's a whole course in differential equations to explore such things. So when you plug your equation in, you're going to have a first derivative. So the first derivative here, if we take the derivative here, we're going to pull down a k and then have a k minus 1 as the exponent. And notice I can leave the k equals 0, because when k equals 0, that k is 0 and I get nothing. So then k equals 1, then I would have the first term here. 1 times a1 times x to the 0th power. In other words, you would pull out that a1. If you take a derivative of this thing, this goes to 0 and you pull out the a1. So there's no harm in letting the k go from 0 on up. Then, if you want the second derivative, we'll let k stay at 0, because when I pull down now the k minus 1. When k is 0, I get 0, and k is 1, I get 0. So no harm in leaving the k equals 0, since the first two terms get you nothing. And in other words, the first derivative would get you here a 0. Let's go ahead and just do that. The first derivative would get you a 0. First derivative would get you an a1 plus 2a2 x. And then the next derivative would get you a 0 there plus the 2a2. So when k is equal to 0, I get nothing. K equal to 1, I get nothing. But then when k is equal to 2, the first term that I'm going to get is going to be 2 times 1, that's this, and then a sub 2, that's that. And then when I have 2 minus 2, their x to the 0 is 1. So there will be no x there. So that's what we get. And then step 2 in my breakdown of the steps, which is my way of looking at it, I'm going to call that fix the exponents. We want all these to be in sync. See, that's k minus 1. That's a k minus 2. So you want to pick, let's say, redefine the index, the summation index, so that the k powers are going to be the same. And I'll show you that by example. I'll show you how to shift k in some terms to make it work. Then step 3 will be the arbitrary argument. When I have everything in sync, all the same k's, I'll be able to pull the x to the k power out, and I'll have here, a summation, and there'll be all kinds of stuff in there. I'll be able to pull that out, and then when that equals, say, 0, I'm going to be able to say that this has to be 0 in there. So that's the idea. This will become fairly obvious when we do an example. And then step 4 will be the recursion relation. We will find a relation that relates the AKs, and typically it would be like an AK, maybe an AK plus 2, written in terms of the AK1, or an AK plus 1 in terms of the previous one, and that'll become obvious when we actually do a case. Now, before we go on, by the way, should probably put a little M1 up here and call this is basically the outline, the method. So the method, you could say the method outlined, or the method of Frobenius is fine, either way. And then here, M2, we're going to look at some equations, or at least one, say, equations encountered in physics. And here's a nice one, where you have the Hooke's law, you have the spring, and you have a mass, and say this is x naught. You can pick that to be 0 as a reference. And then when you stretch it out beyond the 0 point, there's a force, the kx force. F is minus kx. If to the right is positive direction, then this would be in the negative direction, pulling you back. And you can also have friction And one model says that the friction is, we'll call that S sub B, is proportional to the velocity. And that's going to be the opposite direction. So if you're moving this way, then the friction will be to the right. So this we could put down F sub K, that's the spring force. Then when you look at Newton's law, change in momentum with respect to time, and in many cases the mass doesn't change, so we just write down F equals ma. Then the force that's acting on this would be the minus kx and the minus bv. And then if you bring all that in one side of the equation, you would have the differential equation ma plus bv plus kx equals 0. Let's write that as a differential equation. So this acceleration is the second derivative of x with respect to time. The velocity is the first derivative of x with respect to time. And then here we have the constant k times x. So that's the differential equation. So second derivative, a first derivative, and a term with just x. So in classical mechanics, this is often things you're going to get, because you're going to have f equals ma, that's going to be your second derivative, and then you have possibility of first derivative term, and then here a term with x. So you might say this could be a general, say some p of x here, and here I'm going to write the equation in the math style, where I simply, instead of having x and t, in math class we use y and x. In other words, instead of x as a function of t, we'll have y as a function of x. So that means there'll be a second derivative term with some stuff in front of it, plus here, some stuff in front of here with the first derivative, and then some stuff in front of there with the function. So these are the kind of things that we uncover. And actually the Schrodinger equation will be similar, because the Schrodinger equation has that second derivative here with the wave function. And that would be your highest derivative. So that like falls in, and then there's some, plus, v of x like this. And if you have the energy times that, this equation is of this kind also, like second derivative here, and possibly less derivatives, but in this case, you won't have that one there, but that's okay. In this particular case, this still is of the general form. Now, to give an example, a specific example of the method of Frobenius and a differential equation, what we're going to do is we're going to use the example, the Legendre differential equation, which is very important in physics. In other courses, you will encounter the Legendre differential equation. Okay, seems to be that this is the only existing portrait, from the best I could tell. Got some birds here. So let's look at the Legendre differential equation, and we won't worry about the physics here. We'll just do pure math at this point. So you have 1 minus x squared times the second derivative minus 2x times the first derivative plus an L plus 1 times y. So it's like your p of x is this 1 minus x squared. Your q of x here is minus 2x. And your r of x here is just a constant L times L plus 1. And the L equals 0, 1, 2, 3. Very important physics and chemistry, actually. That's a quantum number in chemistry and physics. So when we solve the Schrodinger equation for the hydrogen atom in spherical coordinates, we will get an equation of this form. And the L times L plus 1 will come about, which for the purposes of the math here, we can just call that P. So if we do that, we get the equation in this nice form, 1 minus x squared, second derivative, minus 2x y prime plus p times y equals 0. That's a nice differential equation there. And we're going to solve this one with the method of Frobenius. Okay, here's our differential equation, and we're going to do step 1, series plug-in. So that means for here, we're going to have k go from 0 to infinity, a sub k, x to the k power. See, that's your y. So this is y. Then for this one, y prime, we're going to put in k go from 0 to infinity. We take the derivative, the k pops down. And k can still start at 0 because when k is 0, that's 0. And then this last one over here, the y double prime will go from 0 to infinity, k minus 1, and then have ak and x to the k minus 2. Taking the derivative of this thing, you pull down a k minus 1 to join the k. So let's copy this now. 1 minus x squared. And we put in here this one. K equals 0 to infinity. K minus 1. A sub k. X to k minus 2. Then the minus sign, 2x. And then the y prime one, which is this one. K equals 0 to infinity. K, ak, x, k minus 1. Last one is plus p and this one. So this is going to be k equals 0 to infinity. Ak, x to the k equals 0. So that's step 1. Series plug-in. We plug it in 3 places here because you have 3 places with the y and various derivatives. Now, as part of this step, what I would like to do is, for this piece, put the x inside. So, and for this piece, put the x inside. So I'd rather have here all the x's combining with the x's. So if I do that, this first one, k go from 0 to infinity, will be k minus 1, a sub k, and x to the k minus 2. That's coming from the term with the 1. You just put the same thing down again. But then the next one, I'm going to move the x squared inside. So this is k minus 1, a sub k. Now if I take the x squared inside, that x squared and that minus 2, see that's going to cancel. I'm going to get x to the k. The minus sign is there. AK is there. the k coefficients there in the front. And then this next one, if I move this x inside, I'll have k equals 0 to infinity, k and ak, but then the x will push this exponent up by 1, so k minus 1 plus 1 will be x to the k. Then the last one, there's nothing to do since there's no extra x's floating around. Okay, now I go to step 2. Step 2, fix the exponents. So here I want all the exponents to be the same power. Now I have x to the k, I have x to the k, I have x to the k, they're all good. This is the problem one. So what I'm going to do is I'm going to let k be equal to m plus 2, or you might say I want k minus 2 to be equal to m, and then I'm going to rename that later to k and have it worked out. But for now, best thing to do is just to call that k minus 2 an m. And if I call that k minus 2 an m, then here we're going to go say k equals 0 to infinity. This first term here will have a k minus 1, an a sub k, and an x to the k minus 2. So now if I do this, then when k is equal to 0, m is equal to a minus 2. So what I'm going to do here is say m goes from minus 2, and then at infinity, well, it's infinity. We don't have any problems there. All right, so let's look at that again. K is equal to 0. Well, if k is equal to 0, then m plus 2 is equal to 0, and that means m is minus 2. At infinity, if k is infinity, m's infinity, not a problem. So what is k? K is m plus 2. And what's k minus 1? Well, if k is m plus 2, then k minus 1 would be m plus 1. This is a k, but k is m plus 2. And k minus 2, say that's going to be m. Now the question is, can I start with m is equal to 0? I like to start with 0. Well, yeah, because see, if m is equal to minus 2, you get 0 here. If m is equal to minus 1, you get 0 here. So we can start with 0. So we can replace this with m starting at 0, going to infinity, and then have m plus 2, m plus 1, a, m plus 2, x to the m. Now when you get this far, since this m is an index that's summed over, we could call that j anything you want. You know, L doesn't, you can call it whatever you want. So now at this point, I'm going to call it k again. K go from 0 to infinity. Then I have k plus 2, k plus 1, k plus 2. I just copy the same thing down with the k's. And then this is now going back in for there. So let's do that. Let's write this out again. So this is the first term is going to be here. First term is going to be k equals 0 to infinity, k plus 2, k plus 1. We're just copying this. A to the k plus 2, x to the k. Then we come back up here and copy this one. Minus k equals 0 to infinity, k minus 1, ak x to the k. That is this one here. Then we copy this one. Minus 2, k equals 0 to infinity, k, ak, xk. And then the last one, plus p, 0 to infinity, ak, xk equal to 0. And now we're ready for step 3. Step 3, I'm going to put little quotes around these here, what the heck. The arbitrary, since they're my names for these 4 steps. I broke this down to 4 steps to help remember this whole procedure. Step 1, series plug-in. Step 2, fix the exponents. Step 3, the arbitrary trick. That requires you to pull out the xk, which you have prepared for this step. So now what we do is we go from k equals 0 to infinity, and it's time for big brackets here. We're going to have k plus 2 times k plus 1 times a k plus 2. The x to the k's are going to be factored out. Then this is minus k minus 1, a sub k, then minus 2, k, a sub k, then plus p, a sub k, and the x to the k, which is common to each of the 4 terms, gets pulled out. So here you have, this is copied here. This minus sign here, this is copied there. Minus 2, this is copied here. And p, ak copied there. Now, since this is going to be 0 all the time, you can't count on the x to be a certain value. So that's why we say this is arbitrary. You could put in x for anything, x, or, well, within reason, all right. But the thing is, since there's a variation there, you can put in different values. For this equation to be true all the time, then this will have to be 0. So now we're going to write down this condition here. So that would be k plus 2 times k plus 1, ak plus 2, minus k minus 1, ak, minus 2, k, ak. We're just copying what we have here down there. Okay, so this means here that k plus 2 times k plus 1, ak plus 2 equals, I'm going to put this stuff on the other side. k minus 1, adding to the other side, plus 2k, taking to the other side, minus p, and these all multiply a sub k. And now we look at this thing in here and say, well, this is k squared minus k plus 2k. So that would be k squared plus k. So that's k times k plus 1. So that brings us to k plus 2 times k plus 1, ak plus 2 on the left side equals k plus 1 minus p on the right side. And now we're ready for step 4. For step 4, the recursion, or sometimes people say recursive relation, and that would be a k plus 2. You're basically solving for that. It's going to be k plus 1 minus p, and we're going to be dividing by the stuff on the left here, k plus 2 and k plus 1, and this is a sub k. And I'm going to write this as ak plus 2 equals k plus 1 minus p, and put k plus 1 first. K plus 2 a sub k. So that is the recursive or recursion relation or formula. So now at this recursive relation, we see that the AKs will run wild. They'll go on forever unless at some point, at some maximum k value, that numerator will become 0. So let's say for some maximum k, because k goes 0, 1, 2, 3, but let's say for some maximum k that we will get 0. Now this is elegant from the mathematical point of view because then you're going to get polynomials. From the physics point of view, it's necessary because we can have infinities in there, like when we do probabilities. So very, very essential to have this, but also elegant mathematically to have the polynomials. But that's only going to happen if P, and here's where it's delightful, is L plus 1, like we had when we started. Remember P. Remember when we started the differential equation, P was L times L plus 1. And that's beautiful how that is mathematically elegant, this differential equation, but also that this comes out naturally solving for the hydrogen problem, or actually central force problems in quantum mechanics. And this is related to the angular momentum. So it's a good time to bring back Schrödinger, and we have here Legendre and Schrödinger. Legendre meets physics, mathematics meets physics. So this is very, very important, this relationship. And I'd like to just take a little detour here. This is covered in modern physics and other courses in chemistry. But your angular momentum, your total angular momentum, if we square it, we get h bar squared, L plus 1. We get this. And there's quantization going on, where the L will equal 0, 1, 2, 3. And these are called in chemistry like your S, your P, your D, and it has great physics, That differential equation comes out now naturally from the Schrödinger equation. And in quantum mechanics, you find that you have the L squared, and they show that this commutes with LZ. You could actually do it, but let's leave some things for other courses. That commutes. So, but you can't have these don't commute. If you have, X, and Y, for example, that's not going to get you 0. But since these commute, you can use, for your quantum numbers, you could have simultaneously the quantum number that goes with L, that's going to be little l, and then the quantum number that goes with the LZ, they call that M, or M sub Z. But like in chemistry, they'll have these quantum numbers. They'll have the N for the, say, the orbit, 1, 2, 3, 4, 5, and these are orbitals with the angular momentum. And then they'll have the Z component, and then they'll have spin. So just a little comment there that you'll see things possibly in other courses if you take those courses. Okay, now we're ready for M4. The Legendre polynomials. And when you get this Legendre differential equation in physics, actually this x appears in the form of cosine of theta. That's wild. So it gets really, really rich in its connections. Here we're doing the Legendre differential equation in the abstract, which is this form. But that's the form that will show up in physics. Okay, so here's what we do. We use this recursive relationship and find them. And we're going to find here, the first one's going to be part 0. This will be the zeroth Legendre polynomial. And that's the case where L is equal to 0. Because see, remember your L is 0, 1, 2, 3. That's the way we originally set up the situation, the basic equation. So where an L is equal to 0, then that means P will be equal to 0. If P is equal to 0, then I can go to this equation up in here and write A k plus 2 is equal to, in the numerator, k plus 1. And since the P is 0, that's all I have up there. K plus 1, K plus 2. And there's an A, K here. Notice that we'll get some cancellations going on in here. And we'll have K over K plus 2, A sub K. And the K max here, well, the K max is going to be the case where you get 0, because that's the case we're doing. So what we do here, since this is an even one, and the procedure in mathematics is you set the odd one to be 0, so you don't get any series that will never end. It's just no series there with the odd powers. And that's important in physics too, that we don't have probabilities that go crazy. And here, the A naught will not be equal to 0. And then when you want to find A2, since to find A2, you put K is equal to 0, that's how you get A2. Then if you put K is equal to 0, you get 0. There is no A2. And that means there'll be no A4. For A4, there'll be no A6, and etc. So the polynomial for the 0th case is going to be a naught. Now the convention is, what they do is they want all the polynomials that have various L's, when they put in 1, they want that to be 1. That's the convention. So if you put in 1 for x, since that's a constant, that constant has to be 1. So the 0th polynomial is equal to, the genre polynomial is equal to 1. Now we go 1, the first Legendre polynomial, since that one's the 0th one. This is the case as L equal to 1. Now, when you look at this equation that we have at the top of the page here, I'm going to go ahead and write this over again for you. You often see the P here being replaced by the L plus 1 in this general formula. And that's kind of nice because, see, when L is equal to 0, then your K max, basically you're going to find that's going to be 0. And then if L is equal to 1, then when K is equal to 1, that's going to be your max. You're going to get killed, it's going to be killed off, and then the future ones will be killed off. So here's what we do. When L is equal to 1, we set the even one equal to 0, since we don't want to have the even ones go on for infinity. They're none, there's going to be the odd ones. And since the A1 is not equal to 0, and remember, see, this is going to pick up when you have an even, this will be the next even. This will be the whole even series. And if this is odd, it's the odd series. So for the L equal 1 case, then A1 will not be equal to 0, but then here you want this to be 0, because this is going to kill off when K is equal to 1. So if we do that, then what we'll get is the equation AK plus 2 is equal to K plus 1 minus 1 plus 1 divided by K plus 1, K plus 2. And this is going to get you K plus 1 minus 2 over K plus 1, K plus 2. And that was a personal choice. I mean, you could keep it like this if you want. And then when you have L equal to 1, the P, which is L times L plus 1, would be 1 times 2. Would be 2, and you could then go from here right down to there with the P being 2. But you see, the thing is here is that if you look at this relation, we're gonna go ahead and we're gonna go ahead and do one of these now and see what's gonna happen. If you want to find, say, the third one, that's when K is equal to 1. So then you would have 1 plus 1 over here minus 2 over 1 plus 1 and 1 plus 2 a sub 1. And that's going to get you here 2 minus 2 is 0. That's going to get you 0. So you're only going to have here, for the first one, you're going to have A1, but remember the A1 goes with the X, so it's A1 times X. And if you want this to be equal to 1 when X is 1, then the first Legendre polynomial needs to be simply x. Now, what would have happened if we didn't set a naught to 0? We probably should look at that more carefully. See, if a naught were not equal to 0, then here, if you looked at this equation and you put in, say, a naught for the k, then this would be 0 plus 2 over on this side. And that would mean k is 0. And if k is equal to 0, then you would find that you would have something. There's a minus 2 here. And that means you'd have something for the fourth case and the sixth case, and you'd have an infinite series. And in physics, you'd have be blowups because you have power series go on forever like that. That's not good. So what they do is they kill off that by setting the a naught equal to 0, so that can't happen. And then the odd one will eventually kill off itself, because when k is 1, then you'll have 2 minus 2. See? So that's why they do that. This theme of looking at if it's odd or even and set one of them to be 0. Let's do some more so we can really master what's going on here. That brings us to 2, and that's the second Legendre polynomial. That's the case L is equal to 2. All right. I'm going to prefer here to use the formula with the p. I'm in the mood for doing it that way today. So this is k times k plus 2 minus, we're just writing the general formula over again here so that we can see it, k plus 2. So what's the p going to be? Well, the p is going to be L times L plus 1. So if you have the 2 for the L, then the p will be 2 times 2 plus 1. P is going to be 6. All right. So that means for the second Legendre polynomial, the recursive relationship is going to be k plus 1 minus 6 over k plus 1, k plus 2, and this is going to be a k. All right, now, if you look at this, since this is even, we're going to pick a naught not to be 0, and we're going to pick a 1 to be 0. Now, let me just emphasize why that's important. If we had the a1 here, to find a3, because if that's 1, then this is 1 plus 2. Then if k is 1, you'd have 1 plus 1 minus 6 over 1 plus 1, 1 plus 2. This would not be 0. This would go on, and you could then have, say, a5. If we had a5, that we'd be putting in 3 for the k. 3 plus 1 minus 6. 3 plus 1. 3 plus 2. And this is a3. And this wouldn't cancel. And it's a runaway effect. You're never going to find it to cancel. And the reason why is that here, if k is odd, it'll never cancel the 6, because to cancel the 6, you have to have k as 2. You have to have k to be an even one here. So, because L is going to be 2, that means k is going to have to be 2. So that's where it's nice to see the form with the L, the P replaced by the L. So when you have that form like this, you can see that you're going to have a 0 here eventually. If L is even, K's got to be even. So that means for the opposite one, the odd one, you got to set the first one equal to 0 so that you kill off that series, the odd series. Okay, so let's do that then here. We go now with the even case. So that means A2, when you put in 0 for the K, like this, then you get minus 6 over 2, you get minus 3 A0. Then if you try to find the fourth one, now if you try to find the fourth one here, that's when you put in, remember this is K plus 2, so you want to find the fourth one, you put in 2, but see the 2 and L in this case is 2, so that gets killed. So that means that's gone, and then all the subsequent ones, even ones, are going to be gone. So therefore, for the second Legendre polynomial, we're going to have A0, the constant, and then the A2 is going to be this, and remember A2 hits x squared. So that's what you get, which is A0, 1 minus 3x squared. But if you want put the 1 in, you want that to be 1, that means here A0, 1 minus 3 has to be 1. So A0 times minus 2 has to be 1. A0 has to be minus 1/2. So if A0 is minus 1/2, and this is minus 1/2, then this is going to be minus 1/2 plus 3/2 x squared. So the second Legendre polynomial would be 1/2, and I'll write this as 3x squared minus 1. Three halves x squared minus 1/2. Checks out. Let's do one more. 3 the third Legendre polynomial. So that's the case L is equal to 3. So if we write the recursive relation, in this case, I'm going to put the L in for the P, the L's. Then when L gets to be 3, we'll have the cancellation. So we'll have the cancellations. The odd ones will eventually terminate, truncate. So I'm going to have to set A0 equal to 0 to make sure there's no evens, because this will never be 0 for an even K, since we're counting on K to be 3 to get that to be 0. And that's going to then terminate the series. And that's like a boundary condition in physics. You got to terminate things so you don't get infinite probabilities. Very important in quantum mechanics. So here, the odd one will not be equal to 0, the first one, because that's going to be the one that terminates. This is going to be an odd function. And here we will find for this specific case, K plus 2, we can go ahead and plug in for the L, since that will be a constant for this case. And if you put in L, this P is going to be L plus 1, and that's going to be 3 times 4, 12. So this will be a 12. The P will be, this is your P, will be 12 over K plus 1 and K plus 2, A sub K. All right, so let's find here what happens to, we have A1, find A3. K is going to be 1. So we put in 1 for K, 1 plus 1, 1 plus 2, and this is 1 for K. And this is going to be 2 minus 12 up there in the numerator. Down here we're going to have 2 times 3. So that's going to get us here. This is a minus 10 over 6. And that would be a minus 5/3. So A3 is a minus 5/3 A1. Now notice, if you try to find A5, then that means you have to put in K as 3. But if I put in K as 3, remember, 12 came from L plus 1 when L was 3. So that means here, 3 plus 1, just plugging in for the K, 3 plus 2, doesn't really matter what we do down there. And this is 3. This is going to get you 12 minus 12, and that's going to get you 0. And then all the odd ones beyond that will be 0, because if you go for A7, I don't care what this is. If A5 is 0, A7 is 0. All right, so we don't even care what's in there. We already have terminated. Okay, so that means that the third Legendre polynomial, which is A1, just to remind ourselves that if you have an A1 and an A3, you got this. And here, the A1 will be determined by when we put in the 1 for the x. This A3 is minus 5/3 A1. So this is going to be A1 x minus 5/3 x cubed. So now when we put in 1 for the x, and we want to get 1, that means that here in this case we have A1 times 1 minus 5/3. That has to be 1. So this would be 3/3 minus 5/3 is minus 2/3. So A1 would be a minus 3/2. So if this is minus 3/2, then when you multiply by the minus 2/3, you get the 1. So this means for the third Legendre polynomial, we can write this as this equation here. We could write this as minus 3/2 x minus 5/3 x cubed. And the convention is here, like when you write polynomials, write like the highest order first, the highest power first. So here, we could write this as minus 3/2 x plus, this would be 5/2 x cubed. And then if we pulled out the 1/2, minus 3x plus 5x cubed. And then when we're doing this, we make sure that's an x. since that's the general form, then you would have here 1/2 5x cubed minus 3x. And then when you use this in quantum mechanics, so you replace x with cosine of theta, you get some orbitals in chemistry, all kinds of cool stuff. Okay, so this is more of a technique class to show you the technique of doing this and doing one example well, so that you understand the method of Frobenius.